whiteboard you can also see. Okay, so well, again, thank you. My name is Luewton Agostinho. I am a physicist by formation, also a civil engineer. I have always worked with both in physics and civil engineer. I have always worked with water treatment, but of course, due to my background, I really try to stick to the physical chemical processes. In my bachelor degree, I worked with sand filtration not very long ago. In my master's, I worked with evaporation, so surface reduction, evaporation surface reduction for artificial lagoons. And in my PhD, I worked with thermal desalination. Actually, I worked with a tool to improve the efficiency of atomizers in thermal desalination. I'm currently a lector, water technology at NHL Standen, and the lector in the Netherlands, for those that are not in the country, a lector is a professor from University of Applied Sciences. So the University of Applied Science in the Netherlands are very technical. And recently, in the last 10, 15 years, we also decided to build research groups. And the lectoren, the professors, are responsible for the different research groups we have inside the university. My research group is water technology. And in the focus of our group is physical chemical treatment processes, including desalination, most specifically thermal desalination. But today I will give you an overall view of the desalination technologies. We go a little bit, let me show you. Oh, now I have to do this, yeah. We start a little bit with the desalination why, yeah, so why we need desalination, and then we go a little bit to the desalination how and what. We go very basic on the different ways that you have to desalinate water, and also the what. So what type of characteristics and what type of challenges the system has. I have to say that today I can stay until 10:30 because then I have to go to Rotterdam for a meeting. But it should be enough to at least cover the why and a little bit of the how. And if I'm not wrong, we have a second moment, right, Uche, on the 16th.
16th, Thursday, yes.
Yeah. So, and then in this second moment, we should be able to close. The idea was that in the second moment, I would talk a little bit more about brine valorization. So brine, we use brine treatment because we have now a cooperation with a desalination company, with a desalination plant in the north part of Brazil. And this is the topic that we are working on. So possibilities to reuse the brine. So hopefully I would be able to touch also about this brine part, but let's see how far we can go. So when we start with the desalination why, well, the reason, the why, one of the whys is very simple. So we are all, I guess, very well aware of the difference in demand and supply. So in 2014, our demand was already quite close to our supply in the sense of how much water we need and how much water we can deliver. And in 2030, the predictions is that we are at least at 30% more in our demand. So we need, in general, 30% more water than we can provide in average for the planet. The other interesting. That's a bit annoying that I have this bar here. Yeah, no. If I go back, and now I have to go back, previews, yeah. How can I? Sebastian knows everything about Zoom. Sebastian, how can I get rid of this bar here?
That's only on your screen. We don't see it, but if it's in the way for you, you can move it. You can hover over it, click it on the non-button parts, and just drag it around so that it won't interfere with you.
Yeah. Can you do it? I tried to drag it once, but it just no. That's Oh yeah.
Better here?
Yeah, I think
we-
because there it is sometimes it's covering the
Yeah.
reference.
And this one is okay for you? We can
And
make it-
maybe we can just minimize that.
we can put you here. Can
Yeah.
put you here.
Yeah,
somewhere.
yeah, that would be good. Thank you, Yuri. Well, another why for the desalination is it's also the if you don't only look in a rough way for the demand versus supply, but if you look to the demand versus supply related to how difficult it is to get your hands in the different types of volumes of water, then you see that we are already entering the what we call it the exploitable water at relatively high investments. And at a certain point, if we continue to grow, we will reach actually the orange zone. I think you can see. So the orange zone is really available water, but not possibly exploited. So right now we are in these exploited at expensive high investments. And for example, I give you some example like some reuse. Some industrial reuse, some big complexes like the Aquapol complex in the state of São Paulo. São Paulo has 22 million people, and we have the Aquapol system is actually retreating or treating the wastewater of São Paulo and redirecting it to the industry. More or less the same thing we have here in the north of the Netherlands now. So it's possible, of course. So making potable water out of wastewater, but it is at relatively high costs. Oh, yeah. So another interesting way to think about why we need desalination. I don't know if you guys, it is not a very new report, this water cultivation done by Lux Research in 2008, but it has still a very updated view. I like the view. So what they, if you would like to download this for free as well, and what they say is that to evolve in our hydrocosm, we have to move from a linear, they call it a hunter's mentality, linear mentality, to a more circular mentality. And basically, they say to be able to move to like an ideal situation, we have to tackle three main aspects. One aspect is the reuse, so the circularity. The second aspect, you can see that we have to decrease losses. The losses in the network now, in distribution network now, can go up to 70% in some countries. In the Netherlands, our losses are in the range of 20 to 25%. But we have to decrease the losses, and we have to also diversify the sources, as you can see here. Diversifying our sources means that we have to get out a little bit of our bimodal matrix, which is basically surface water and groundwater to serve water, and we have to exploit other sources. So desalination enters in the source diversification, because as you can see, 98%, 99% of our sources are now still based on groundwater and surface water. Seawater has been increasing quite a lot, but still compared to the volume that we have from groundwater and surface water is not comparable. So we have to move from this bimodal source, groundwater, surface water, and we have to adopt a little bit more like we have in the energy demand. We have to diversify our sources and find other ways to supply water. But okay, so when you think about let's use desalination, let's start with desalination. The first thing you have to think is what is actually desalination? So desalination is basically the technologies that remove salt from water. So you can get a salty water and you can remove the salt and then distribute to the population. But to be able to understand this, it's also important for us to know what we consider in the water technology domain, what we consider actually salt water. So, well, we say that for us, water technologies, fresh water is water with a concentration below 0.5 ppt. So if you have below 0.5 ppt, this water can be distributed. So according to United Nations, according to European legislations, according to American Water Association of many different countries, so if you have a concentration below 0.5 ppt, you can distribute this water to the population. So it's fresh. If your concentration is between 0.5 and 30, then we say it brackish water. So where you can find brackish water, do you know? where you can mostly find this brackish water? Rivers can be.
The river meets the ocean.
Yeah, in the region where you have the deltas, we call it, when the river meets the ocean. But there are other sources that you can directly find it. Groundwater. Yeah, so there are many groundwater sources depending on where you are. For example, in semi-arid region, because normally it is a very crystalline soil, and when the water percolates, it is also a very salty soil. So what you get is mostly in this groundwater, in semi-arid region, you get salty water. So you would not think, but for example, the whole northeast part of Brazil and the west coast of the United States, where they try to solve their scarcity problems by digging wells and getting groundwater, which is a quite easy source because it's already filtered by the soil. But they most of the time get surprises that when they pump the water out, the water is salty. Salty, it's brackish water. So at the end, removing the salt, it becomes quite a tricky problem as well, because it's not. We have in the Netherlands, for example, here in the region of Friesland, our groundwater is not salty, but it's really rich in iron and methane, for example. And well, aeration solves your iron problem, and also deaerate with methane. That's okay. But salt, it's a dissolved, non-precipitatable oxidation type of earthy metal. So it has to be done really via a thermal process or a membrane process. It makes the use of brackish water quite complicated in many different locations. And then we say that water is saline or salty when the concentration is between 30 and 50 ppts. By the way, for the non-chemist, ppts means in grams, milligrams, micrograms per liter. The students? When we talk 30 ppt, what I am talking, grams per liter, milligrams per liter. Yeah, we're talking about parts per. No, that's trillion, T. No, sorry, not trillion, 1,000, parts per 1,000. Parts per 1,000, then is?
That says milligram per milliliters?
Now, parts per 1,000, parts per 1,000. So this is parts, that is grams per liter. So if you have 30 to 50 grams per liter, then you have saline water. If you have below 0.5 grams per liter, then you have fresh water. And you can normally do this also. Oh, if you have above 50, which is not found, you cannot find this in nature. There are no surface or groundwater sources that can give you above 50 grams per liter salt. Where you find them? Why we then define this also in the saltiness scale? You cannot find in the sea. No sea has this concentration. Also, no brackish water, no river. Where you find this water then? In the industry, but also in the desalination plants, right? Because when you desalinate, you get seawater, let's say, then you get 35 more or less. And then you normally do freshwater 50-50. Let's say that you do 50-50. So in one side, you have water above 0.5 that you can distribute to the population. And in the other hand, what you have a concentrate, a brine, that can go up to close to 70. And that's what we call the brine. And normally what we do with this brine, do you know? Yeah, you bring it back to the sea. Right now, I will show some slides. Like right now, 95 between 93-95% of the plants, they are just dumping back. But legislations are also changing about that. But why we have salt in the, this is the salinity plot of the earth. So what you should see is that if you get a little bit to purple, then you get low salt concentrations. And if you get a little bit to dark blue, actually even in the green zone, you get a little bit more salt concentration. So I have to go up. So here is low salt concentration in the zones, in the dark blue zones here, in salt streets, that's all. So why we have different salt concentrations in the sea? Do you know? It's temperature based. Basically, it's temperature based. I actually also show this plot here. So you see that when you have higher temperatures in the equatorial zone, you of course also have more evaporation. Evaporation means concentration of the salts. So you get high salinity in this region, up to 35 indeed grams per liter. But you can see, for example, here in the Chilean coast, for example, here a little bit in the Chilean coast, where else? A little bit here also in this coast of the United States, even though I'm not really very inside the high equatorial zone, I still have quite okay salt concentrations, dark blue. And why I have this? What could be the other source, if not only evaporation? And from where?
On land, wherever there are rivers.
But then you have then it reduces the salt. Every time you have river, you would have this. And that's not very true, because you can see that, for example, here in the Amazon forest, you can get one of the biggest rivers on the planet. You get low to 31. But this salt concentration has also to do a lot with volcanic activity. So volcanic activities, volcanoes are also very big source of salinity. Well, another thing that it's interesting to get to know is the seawater. If you get seawater, the composition is only 3.5% or 35 grams per liter of salt in average. But it's if you take a look on which kind of salts you have, then 55, 85%, 86% is actually sodium chloride. And then you have a very okay percentage of around 80% of sulfate and magnesium, and then all the other constituents. But well, impressively enough, these are the guys that make our life difficult when we want to desalinate. Most of them, especially sulfate, calcium, because of the precipitation of the membranes, and magnesium as well. But in general, what it's interesting to show to you is that 85% of everything is sodium chloride, and most of the treatments are based on the removal of this specific salt. We have also what we call minor constituents below 1%, but these minor constituents are very long. They were some researchers were, and they still don't do it. So looking into them as a valuable metals, you can have quite some valuable metals there. Platinum, you can have iridium, but so true that we started a few years ago what we call it the sea mining. Wetzel still has the discussions in the desalination team, which would be movements where you can actually use the sea to recover gold or many different types of valuable metals. But of course, if you would do this simply for the fact that you want to get the metals, it doesn't justify economically. If you are desalinating water and you already have this brine and you have to do something with this brine, it's a different discussion. But if you are doing this for the metal itself, the energy that you have to put in your system for these minor constituents, it's bigger than the amount of money that you can make with it. Okay, so this is more the desalination why, so the constituents, what we have in the sea, where you can find the salt concentrations. And then let's move a little bit now to the techniques itself. Basically, you should see a desalination technique as a separation. So what you have is you have a feed water where you have the salts together with your with water in, and then you have to put some energy in the process because this is, of course, this is an energy demanding process. So you have to put some energy. And then when you put an energy, you divide your inlet into sources. You divide it in a water product, a distillate or permeate that you can distribute to populations, you can use in industry, whatever. And you have a rejected water, what you call it, normally call it brine. So that's normally how it happens. Depending on the technology, this fraction changes quite a lot. For example, for thermal desalination, you'll be amazed, but this fraction can be up to 10% of. So you have 100 liters in and you only get 10 liters of fresh water out. But of course, because on top of all the water that you put in, you also have what we call the cooling circuit of thermal desalination that takes 80% of your total water feed. I will show also some slides later on. But normally for a vessel osmosis systems, for example, this fraction is 50, more or less. So you put 100 liters in, then you get 50 liters potable water, treated water, 50 liters brine. And depending on the energy that you put, thermal, mechanical, electric potential, then you define your type of separation unit. So, well, desalination is actually a process that happens in nature. So, in the ocean, you have evaporation, and then you have advection, condensation, rain. When you have rain, it's already fresh water. So, just to show you that it's a process that exists for very long. And actually, if you go to the book of Aristotle in 384, 322, it's a book, it's called Metrology. Aristotle, in his book Metrology, he said, salt water, when it turns into vapor, becomes sweet. And the vapor does not form salt water when it condenses again. This is known by experiment. So Aristotle, in 384, 322, before crisis, he already tested thermal desalination. And further on, in his same book, he says there is more evidence to prove that saltness of the sea is due to the admixture of some substances he did not know back then. Besides that which we have adduced, make a vessel of wax and put it in the sea, fastening its mouth in such a way as to prevent any water to get in. Then the water that percolates through the wax sides of the vessel is sweet. The earthness stuff, the admixture of which makes the water salt, being separated off, as it were, by a filter. So Aristotle, in 384, 22, he tested both thermal desalination and membrane desalination. Because here what he did is just get a vessel, a wax vessel, and then he closed the top, and then he put it in the sea. And then water was percolating inside via the wax walls. And then he was tasting the water that was percolated and it was fresh. He said, whatever is given the salt to this water, when it percolates, it stays out. So it is not, of course, not a new idea. If you check in the literature, at least as far as I am informed, I did a long patent and literature review during my PhD. The first patent ever probably published about desalination was done by Della Porta, Italian scientist, in his manuscript Magia Naturalis in 1558. He actually described a thermal desalination system where he was using the solar energy to get the salt out of the sea. As far as I could see also in the reviews, maybe the first desalination plant ever built in such a scale, let's say large scale, was built in Chile in 1872. Las Salinas, it was a mining field, and it was done by the Swedish engineer Charles Wilson. He was just doing solar steel. So he was using glass So with a certain inclination, a certain angle, and via thermal insulation, he could evaporate the water, condensate on the glass internal surface, collect it back, and he could back then produce 22 cubic meters of fresh water per day with this simple system. It was a 4.4 thousand square meters, and it was done to provide water to the mining employees, to the mining workers. Okay, but if you try to see the amount of possible desalination processes that we have now, there are quite a lot. So I like to separate them basically in the thermal energy systems. And these are the systems that I worked during my PhD. So systems that use a thermal source to evaporate and therefore to remove the salt from the water. And let's say you can get to the mechanical chemical energy. Let's say thermal, non-thermal, because this corresponds to a quite small fraction, excluding, of course, seawater reverse osmosis taking the market right now. So by far the most used system. So basically, if you look to big plants, to serious things, you see reverse osmosis and you see thermal desalination. So the very, very big plants for human consumption, production, then you will find these two. But there are many different ones, especially when you look to thermal energy, you have multi-effect distillation, multi-stage flash distillation, thermal vapor compression, TVC, solar distillation. For membrane, you have reverse osmosis, you have MVC, which is a combination of thermal and membrane. You have electrodialysis, which work a lot with this electrodialysis, but there are different types. Well, if you compare membrane with thermal, membrane is a physical process. You just use the osmosis balance, so nothing very new about it. And the thermal process is simply that you apply heat. By applying heat, you evaporate and then condensate again. But of course, you let your salts behind, because when you evaporate, you just evaporate your liquid fraction. So when you think about thermal and membrane, these are basically the two types of processes that you can have. And if you look to the percentages now, when I was doing my PhD, this was already different. Thermal desalination, reverse osmosis was gaining force, but you can see now that reverse osmosis represents 69% of the market, more or less now. So this is a report done in 2021, so it's not very old report. Maybe we already increased that by few numbers of percentage, but what you have to see is that reverse osmosis is the dominant one. After reverse osmosis, then you have MSF, that's a multi-stage flash. I will talk a little bit about, and you also have a very good part of MED. These two guys here, which corresponds to 25%, they are there because in volume, they are huge. While you see some desalination plants done for 1 million people, for 500,000 people city, for MED and MSF, you can easily find plants for 5 million, 6 million, 7 million. So it started with these guys. It started in the Gulf region, in the Arabic region. It started with these guys. They are monsters, very big, very robust plants. And they are really the largest that you can find in the market. I'll show another plot that you see. And when you also still compare with membrane and thermal processes, you see, all of these guys you see at the end of and in the beginning, they are thermal. And here I give two examples of membrane technologies, electrodialysis and reverse osmosis. There are very critical differences. One, of course, is the operation temperature. So the thermal desalination processes, they all work with the temperature of around 70 degrees, to be able to produce the fresh water. And while the membrane processes, they work with thermal, with ambient temperature. Another thing which is very important to see, as I told you, is that the thermal guys are monsters. It's like you should compare. It's like comparing a truck. Thermal desalination system is a truck, and a membrane, well, at least what you see now, the membrane systems are more like a normal car. So you can see that the thermal desalination, they start with 50,000 cubic meters per day. They start with more or less like that, while you can have EP and RO with up to 2 cubic meters per day. Electric consumption, it was very different before, but reverse osmosis has been quite competitive now. And the thermal energy consumption is also, of course, much higher here, but you can only justify for the thermal processes if you are close to a thermal source, to a refinery. Mostly we use it also in offshore oil pumping stations, sea oil pumping stations, because you do have your outburst gas that you have to burn anyway, so you can. The quality of the distillate is not that different, but in thermal desalination you can still get, very, very good water. And the unit, the cost per cubic meter is also something that we will come back to that. In thermal desalination, you can now, MSF especially, that's why it's the large project that you see there, you can produce at 0.5 to $1.75 per cubic meter, which is, as I told you, when I started my PhD, the lowest number you could get with RO was in the 1.5 to dollars per cubic meter, but now you are actually in the 50 cents, which was the goal back then. The goal of the reverse osmosis was to get. So what do you think? Is this very expensive still? 50 cents per cubic meter? How much do you pay for the water that you use in the Netherlands? And it's not seawater. By the way, here in Leeuwarden, you know which kind of, from where we get our water in Leeuwarden? Which source it is? It's groundwater, yeah? Which is quite okay-ish to treat. Quite, as I told you, our problems are iron and a bit of methane. But it's quite okay-ish to treat. But do you know how much you pay for the water that you have now? Cheaper than that. Okay, I'll show you, because I was actually, is that? Oh yeah. Oh yeah. Yeah, here it is. I was actually yesterday, I was trying to get some numbers, and I made a copy of my Vitens bill. And I was, but strangely enough, the bill that they sent to you per month, you cannot find the price of the cubic meter. They don't say it. So I had to go to my jaarrekening. I had to go to my year summary, and I was looking all the way, and I could find. So here for my water, I pay 66 to 78 cents. Depends on, of course, the period. It increased a little bit the last years due to the energy cost. But as you can see, can I go back now? How can I go back? Previews, I think. You can see that solar pump RO, meaning RO powered by solar energy, powered by solar energy, you can get to the same cost. It is as cheap as groundwater treatment. That's why desalination is taking a very big fraction of the market. And I repeat to you, maybe the easiest source, depending on where you are, of course, but one of the easiest sources to treat here in the Netherlands, I would say it's quite easy, is groundwater. Of course, in Bangladesh, you have a lot of arsenic. In the semi-arid region of Brazil, I told you we have salt in our groundwater. But here, yeah, iron and methane, of course, you have to take into consideration some pesticides, which is coming, and PFAS, now it's coming to the picture. But I mean, well, just to show you the values. And then coming back, when you compare membrane and thermal costs, so do you guys know what capex is? Yeah, the students, do you know what capex is? No? Well, if you have a plant, if you have a big water plant where you have a lot of different things, for example, you have your energy, you have your chemicals. If you have all your costs, chemicals, you have people that you have to pay. So if you put all these costs, on the table, then you have what we call it the amount of money you need to operate your system, to operate it. This is your OPEX. This is your operation costs. How much money, if you have your plant is already running, and then you say, okay, I need this for energy, and then this to people, and this to chemicals, this is your OPEX cost. But before you operate, you have to build, right? You have to put everything in place. You have to get your machines, you have to get your land, you have to build everything. The money that you need to build is your capital cost. So it's how much you need to build, how much you need to operate. CapEx and OPEX. Okay. So when we see, thank you very much. It works. I think maybe with the camera that would be we would use that for the next one. Yeah. So if you compare membrane and thermal, being A thermal and B membrane, and pay attention, please, that I'm trying to make all of. It's always a comparison between these two because they are the two ones that are dominating the market now, right? So if you compare the thermal to B, in the thermal process, 75% is on construction for your CapEx. And the BRO plants, 60% on. The capital cost, sorry, for the capital cost. So 77% is on construction, and for construction RO only 60%. So you spend more money. And then in membrane systems, the second part is in the engineers, the project. While now for the thermal process only you pay only 7% about that. Why? Because this, as I told you, these thermal processes are very old. So the engineering behind it, it's quite straightforward. Many companies can do this. But then when you go to OPEX costs, oh, sorry, I made a mistake in the title. These are OPEX. When you go to OPEX cost, then you see it's very different from thermal to RO. Now in the thermal, of course, 52% of all the energy you use to operate your system is thermal energy, while in the RO plants, 41% is the electrical energy. So it's more or less a balance between electric and thermal. And then you also have a very large cost for the chemicals in the membrane side because of the membrane cleaning, while these chemicals in the thermal desalination only corresponds to 4%. So this is in terms of sustainability and in terms of let's say footprint of the thermal process is much better. Why? Because when you put chemicals in to clean your membrane, or when you put chemicals in to run your thermal process, where these chemicals are going at the end? To the brine, right? To the brine, to this fraction, to the 50% brine fraction, and eventually they are discharged in the sea. So one of the main problems that we have now in the brine, one problems challenge that we have now in the RO brine is how to tackle the chemicals, how to the chemicals discharge, among others, of course. Let me check the time. Yeah. So and then now, if you would see, if you would check where the big desalination plants they are. So of course, as I told you, more or less everything started here, and you will see that in this region, of course, due to the scarcity and the proximity of the sea, they really had to go to desalination much before than we thought about it in the United States and in Europe. And as I told you as well, this started many years ago. It started somewhere in the 70s, 80s. So most of the processes that you see here, they are thermal processes. And then you see a very large production. If you see here, this production of thousands of cubic meters per day. In the States, we have now a very large fraction of the whole market in the world right now. And basically in the States, we have the reverse process. But you can see very well that it's more or less spread all over the planet now. And of course, this is from 2000. Yeah, this is the Pacific. For 2009, it's not a very updated because you can see even now in Brazil we have a big plant being built in the north part of Brazil. Also, we have a plant in the south part in the region of São Paulo now. So in the South America, it's much more present as well. The purpose, if you think about what is the main purpose is still drinking water. that you do desalination. So 60% of everything you do is is for drinking water. But you also have a very nice fraction for industry, 36%. So especially industry in the Arabic region, but many other countries right now. And you have then the tourist military, they correspond to not more than 10% of all the other purposes that you have. Some figures. Well, from the Smart Water magazine, that's more updated than the plots for the IDA. It's from 2021. We have now about 18,000 desalination plants built in the world, with $6.6 million in capex in 2021. We have $11 million of OPEX. So we have invested $6 million in construction, and we invest in 2021 around 11,000 millions in OPEX costs. So we have 6.3 million cubic meters per day produced of water, and we have 79 cubic meters per day of operating capacity in 2021. The Persian Gulf, as I said, is the one that has the largest fraction of this production, and the United States comes in second, especially the Texas region, the West Coast region of the States. So this is a more introduction part. Now we can go to the more technical part, and we have half an hour to go. Should we give a 5 minutes break and then I can grab a coffee? Sebastian, what do you think?
Since we're anyway only having this until 10:30, you said,
Yeah.
maybe we'll just continue, complete the hour, and everyone can leave on time.
Yeah, it's okay. I just really need a 5 minutes break because I have to go to the toilet and I come
Yeah,
back.
of course. So then see you again in 5 minutes.
Yeah, I do it very fast. So
Sure, of
see
course.
you in 5. Yeah. Can you hear me now?
Yes, all good.
Also see me? I think so. Huh?
Yes, we can see
Okay.
you.
So now we finished the intro. We explained some terms, some numbers. Now we start to go a little bit more technical, so you can learn about specific efficiency numbers and some specific terms that we use. So let's start with. Okay. Yeah. Well, what we have said before is that desalination is some kind of it's a thermodynamic. Let's call it a thermodynamic process. Of course, the term thermal in thermodynamic always imply a thermal energy. But a thermodynamic process, if you get to the second law of thermodynamics, it simply means a process. It's a process efficiency or process functioning type of system where you have to put your feed in, you put some energy, and then you get two different types of sources out. You get a treated source, which we call it distillate, or we call it permeate, and you get a concentrated source. So normally you see here that this is a diagram that I used in one of the courses I did of thermal desalination. Actually in Spain, in Almeria, they have a very large solar platform there. And then you can see even that the blue arrow is much thinner than the red arrow, which indicates that normally your brine, and your brine fraction of volume is larger than your permeate. And that is really the case. Most of the time is the case in thermal systems. In reverse osmosis system, as I said, it can go 50-50. Yeah, depends on your initial concentration. Yeah? Just for you to understand, you can tackle desalination. When you start to learn about it, you can tackle desalination in two different types of variables: the N variable, which is your mass, and the omega value, which is your salt concentration. So you can use both of them. When we see MCW, it's the mass of your seawater or your feed. Sometimes it's also represented as F. When you have MD is your distillate, and BD is your brine. And that is the same for omega, because then you have seawater, distillate, and brine. But then in terms of salt concentration, in mass we use kilograms. Your mass flow, in this case is related by flow, is normally expressed in kilograms per second, and your concentration kilograms per kilogram. So kilograms of salt per kilograms of volume that you have in your water. Independent on the type of process applied, adopted, desalination transforms seawater into concentrate, brine, and distillate. So if you think, normally it's a mass conservation. So the mass or the flow, whatever, you can also express with mass if you consider the same time, of course. Your mass or your flow that enters the system, so your mass in water, is the same amount of mass added from your brine and from your distillate. It should close. And while the leakages in such processes and the accumulations in such processes are very small. The salt conservation holds for the same. But normally when you do salt conservation, if you want to close your balance, normally we do the salt conservation based on your mass as well. So here you have kilograms per second, kilograms per kilograms. So what you're going to have is a kilograms per second of salt entering your system. This should also balance. So you also should balance this. Now, again, salt concentration is in kilograms per kilograms, and normally mass concentration kilograms per second. Normally, we use very specific concentration factors. So it's interesting for you to know. One is the concentration factor itself, which is basically the ratio between the concentration of your brine divided by the concentration of your seawater. So, for example, if you are treating your system with a 50-50 ratio, and then you are putting seawater in with 35 grams per liter, and you get your brine at 70 grams per liter, then you have a concentration factor of 2, right? So concentration factors of 2 means that your brine, salt concentration in your brine, is double of what you get in your seawater. And that's normally the case, as I told you, when the balance closes, there's normally the case for a 50-50 system. What you can do as well, if you can combine the equations, and then let me see if I can quickly go back. It's a little bit. So if you use your concentration factor and you combine this concentration factor with the normal salt conservation, then you can get a relation with your mass as well. So the mass of your distillate can be calculated by the mass of your seawater times the inverse arithmetic of your concentration factor. And this is normally very interesting because the technical aspects that you're going to get from the construction is normally, this is a number that you can easily calculate. Why this is a number that you can easily calculate? Because this depends on what kind of system you're building. So, for example, if somebody would come to you and say, I want you to use your plants to desalinate water for the city of Luewton, how much would be your MD? Do you know? How much would be your MD? You can do it by head. Easy. If somebody would tell you, hey, I want a plant to fix water to the city of Luewton, how many citizens we have in the city of Luewton? 100,000 per day. Exactly. 100,000, which means how many citizens have the power? 5. Right? If somebody would ask you if you build a plant to the city of Luewton, you would think, I have 10 to the power 5 people. And in general, a person drinks or uses how much? One person uses more or less 100 liters. Let's just facilitate our life. 100 liters per day, right? More or less. So if you use 100 liters per day and you have 10 to the power 5 people, if you want to desalinate water to the city of Luewton, you have to produce an MD, which is 10 to the power of 7, right? Liters per day. So your plant has to produce 10 to the power of 7 liters per day, in average, of course. But that's a very simple calculation, of course. because when you start your calculation, that's the first number that you should get. That's the first number you should get. But there is a problem with this number, because cities are not in 20 years time from now, do you think we still have 10 to the power 5 people? Of course not. Cities are not static, right? Cities grow. So if Martin comes to me, and Martin is the mayor of Leeuwarden, and Martin say, and I am the desalination constructor, and then Martin comes to me and say, Luewton, I want you to be the desalination plant for my city. And I get to I ask the mayor how many people you say 1,000, right? And then I go and do a calculation of a plant of 10,000 to the power of 7 liters per day. In 20 years, I have a problem, right? 20 years, I have a problem because the city will grow. So you start with this number, and then you apply what you can apply if you are a smart builder. You apply the same. I will get back to the mayor, to Martin. I will say, oh, Martin, can you give me a population growth curve of the city of Leeuwarden, right? In the last, well, as long as you have back, in the last 100 years. So by the population growth curve of the city, I can predict how many citizens I'm gonna have in 20 years time. So I actually build my desalination plant based on that. And you're gonna be amazed, but plants are indeed built in this type of lifetime, between the 20 and the 50,000, because for the mayor, the investments are very large to construct for 100 years. You do have to save space, of course, for expansion, but you will build now to operate at least 20 years without problems. So that's why the MD is very easy. But of course, if you can do the MD, and then you can also Martin, if Martin is very when Martin is very smart, and he's a good mayor, and he has a sustainable eye. Martin will say, Luewton, but I don't want a concentration factor of 2. I would like to have a concentration factor of at least 1.5 or lower, because I will discharge this water in the sea, and I want to have very, very, very low impacts. So you can start with this, and you can start with that, right? And based on this and that, you can calculate easily your feed volume. And then it starts, because then you have to calculate the pump capacity, you have to calculate the system capacity, and so it goes. And of course, I told you this concentration factor, it's like, oh, do it to 1.5. But sometimes you cannot, depending on the technology. You say, if I do it 1.5, I'll have problems, Mayor, because your energy cost will be very high. It has to be a playing game, right, with the energy cost as well. Okay, concentration factor, production rate, actually, it would be best to concentrate as much as possible, right? Because then your brine volume decreases, even though it's a very concentrated brine, but okay. But if you think also in the concentration factor, that's also another interesting thing. That is
No, within that piece of the whiteboard.
Oh, okay, this. Okay. Yeah, then you can see, yeah. So you can think about your concentration factor in the following way. You are putting 100 liters in, and then you're gonna get 50 liters treated water or distillate, and you get 50 liters brine. So most mayors, there are mayors with other mentality. So some mayors can come to you and say, okay, wait a minute. For every 100 liters that you get in sheet, you just give me 50 liters of distillate. No. I want you to have 80 liters of distillate and only 20 liters of brine. I want you to decrease as much as possible. But what is the problem with desalination technologies if you do this? If you increase this ratio compared to that one, it means, because the concentration that you get from the sea is the concentration you get from the sea. And normally, I repeat myself, this is the 35 grams per liter, right? This is it, normally. So if you do this balance, and you increase the total water production in detriment of what you produce of your brine, it means that you're going to have low volumes of brine, yes, that you discharge to the sea. But this will be highly concentrated, really, really. And then very easily, you can make your calculations as well. If you remember of the saturation curve, of concentration saturation curve, you will see, you will see very quick that you can reach saturation here. And if you reach saturation here, what happens in your system when you try to back the water to the sea? Precipitation of the salt in your pipeline, precipitation of the salt in the system, and then very soon you're gonna get to change all your pipes. You have to change your tanks. You have to change everything. So this is a problem. You cannot go very high in concentration, because then you have falling. Scale precipitation in two bundles are more frequent than the more the salt is concentrated, especially when you see. Maybe it's not very easy to see. I don't know if many of you guys have seen with your eyes a thermal desalination plant before, but a thermal desalination plant can be as big as this building, as this whole building. It's huge. So imagine that you have to imagine that you have to change. Imagine that you have a concentration of salt inside the tubes. It's impossible to get in. The salt crystallizes, it becomes a big rock, and you have to throw the whole thing out and then buy a completely new evaporator, you know? So you have to avoid at all costs this type of precipitation. So going very high with your recovery or your concentration is normally not a good idea. Experience with all systems indicate the need for a scale control, of course, due to that. And as I told you, these guys are not really, do you remember? These guys are not really the most concentrated ones, right? We did see which one of these come after the sodium chloride. Which one is the first? This guy, yeah. And then after that guy, the magnesium, right? So they are not the large concentration of salt you have, but they are the cause of your problems. Yeah? Most of them are the cause of the problems. So scale restricted flow class reduces heat transfer and causes outages, especially when you have to have heat transfers. Concentration factor, production rate for our systems are normally different from thermal system. Typically, the recovery rate from seawater with reverse osmosis is between the 38 and the 45. So this is a typical working desalination seawater with desalination plant. And you can also, I told you about the CF. So the CF is the relation between the amount of concentrate you have in your brine divided by the concentration you have in your feed. So this is your concentration factor. But another term, another coefficient that we use a lot in desalination is the recovery rate. Right? And the recovery rate is exactly the inverse of that. So what you do is to divide basically the total mass of your permeate or your treated water, the mass of your seawater. Remember, this is flux. I have an M here, but this is flux. And then what you get is your recovery. So your recovery is basically how much water you recover, treated water, based on the total amount of water that you can in. So if you put in 100, and you get back 80, then you have an 80% recovery rate. So 80% of everything you put in your desalination plant becomes potable water, becomes usable water. Yeah, and then you can start to play. I have exercises about that. Normally here I stop. I give you some practical cases and I ask you to calculate the plant and to calculate the coefficients, to play with the flows, everything, but that's not actually the intention of this course. I just present the possibilities to you. Later on, I'll give the presentation to Uche and also to Jordi, and you can look at home, and then if you like the mathematics, and if you like the calculations, because I mean, as I told you, I'm a civil engineer. So basically what we learn when we learn water technology is that we learn how to build these plants. So these coefficients they are very important for us because they help us to attend the mayor when the mayor comes to us, build this plant for my city. So we have to go with these coefficients to be able to build everything. Okay. So the concentration factor, so if you, as I told you, if you have a reverse osmosis, for example, system that has a recovery rate of 0.45, then you have a concentration factor of 1.82. It means that your brine salt concentration is 1.8 times bigger than your feed water concentration, right? So if you start with 35, you're going to be there in the 60 grams per liter end. And then you're going to have 45% of recovery, which means that for every 100 liters that you put in your system, you get how many back? For every 100 liters that you put in your system, you get here how many liters back? If your recovery rate is 45, then 45. So you put 100 liters in, you get 45 liters out, treated, and you get how much, right? 55, right? And this 55, 45, when you do the salt mass balance, gives you a concentration factor of 1.82, means you start with 35 grams per liter of salt and you end up in your brine with approximately 60. Okay, so a little bit lower than 2. Yeah, so to give you some ideas of how these two ratios work for thermal processes and for reverse osmosis processes, this is a nice table. For example, your concentration factor in all these three guys, they are thermal processes. All these three are thermal. So 1.4262. And so this is what you get in concentration factor, and this is what you get for RO. The problem is here, as you can see, right? So you can see here that the recovery rate of MSF, multi-stage flash, can be between the 30 and the 5. What does it mean? Recovery, the 30 and the 5. It means that for MSF, sometimes, pay attention, I am putting how many liters inside my system? And I'm getting how many here? Between the
5 and 30.
Yeah. So I can put 100 liters in, and I'm getting only 5 liters back. That's crazy. That's crazy, right? So for every 100 liters that you put in your system, you only get 5 back. While in reverse osmosis, this means 35, 45.
Isn't the type of thing to be 50 because if you look at the concentration factor, it says 1.42.
Oh, could be, but no, but it could be that low. It could be 5%. I will explain to you very soon. But if I compare this is a good point. Thank you for that. I will check this table. But I will show you why we can get so low recoveries here in thermal. And that's the next slide. Just a minute. Yeah, this is the problem. Normally, don't look at that. Just look at this. Normally, in reverse osmosis, what you get? You get 2.4 to 3.2 cubic meters per hour in. And then you get 2.3, 0.1, 0.3 for the pre-treatment, okay? But then look to this final number. For every, you can round this to 3. Let's round this to 3, right? So you put 3 liters in, 2 cubic meters per hour in, and how much you get out? 1, right? How much you get? This is fresh water. The blue one's fresh water, the light blue, and the dark blue is concentrated, okay? So you're putting 3 liters, let's call it liters in, you get 1 liter out permeate and 2 liters concentrate. What is your recovery rate here? 33%, 30%, which matches that table, right? But look to a thermal desalination system, how it works. A thermal desalination system works in the following way. You're putting 10 liters in. 10, huh? And then this is how much you get permeate. 1. This is no more than, that's just 10%, right? It's 10%. This is 10. This incredibly low. But why? Normally, we mix this up because you see, from these 10 cubic meters that you put in thermal desalination, you have a whole 8 cubic meters that is only for cooling water inside. This is a closed cycle that you need to keep for the cooling water. You know, that you can simply re-inject. So in fact, you should not see this. You should see 10 minus 7 liters of cooling gives you how much? 3. From these 3, you get 1, which is, again, 33%, right? So one should not mix the cooling water fraction in the thermal desalination system with the production factor. Yeah. So normally membrane guys, when they want to compete, they use these numbers for thermal desalination, but that's not really true. But of course, this cooling water time has to be recovered at a certain point, cannot be infinitely recirculated, right? So at a certain point, you have to refresh the cooling water, and this causes an impact in that production here. But it can be there so low as 10. That's why I said maybe the concentration is because it could be between the 5, 10 to 30% if you consider the cooling. Okay. Time? Okay. So we should stop here. Maybe I have to go back to see Sebastian. Sebastian, can you see me?
Yes.
I stop. Yeah. So, guys, maybe you can put your camera on, then I can see you if you are still alive after 1.5 hours. So, I mean, we are very close now to finish this first part. I think I have, I don't know, maybe something like 10, 15 slides or so. And then I can start with specifically the brine recovery part. I give you some examples, but that will be then Thursday in the afternoon, right? And we start at 2? 2 o'clock. Okay, I'll be a bit before because then we can check all the things again, and then we go from 2 until 4 o'clock. So we should be able to close this part here and then talk a little bit more about the specifics of the brine. Any doubts so far, guys?
Tuesday, I have in my calendar 1 o'clock in the afternoon.
Okay, what? Then it's 1.
But just to make sure that that's all right, that's the right.
Let me double check. And,
I'm nodding yes. Should be at 1 in the afternoon.
Yeah.
1 o'clock.
Yeah, 1 o'clock. Yeah, that's what I have in my.
Right.
Okay,
Perfect.
so it's
perfect. Just so we don't get it mixed up.
Yeah.
Right.
1, 2, 3, and then I should be able to finish this part. Any questions so far? No. Uche, yeah.
Is different desalination technologies? Is there any difference in selectivity of salts? So sodium chloride versus a sulfate, for example.
Yeah, in the thermal desalination processes, normally no. What you produce is distillated water, so it's really water free of salts. Yeah? Some techniques, for example, like the techniques that do what we call it air to water processes, they could remix the concentrate with the permeate because it's simply water, not that many other contaminants like in seawater, and then they can provide this via remixing. But normally thermal processes, no selectivity whatsoever. But membrane yes. Yeah, and then if you use the thermal heat process, like say no, but if you use eutectic freeze, for example, or if you use supercritical desalination, actually, it was actually a thesis also. You can have access to this thesis, the thesis of Ingo Loisbrock. He proved that if you change a little bit pressure and temperature, you can reach different salt concentrations. So, for example, sodium you reach here, magnesium there. So, in steps at different pressure and temperature, you can selectively precipitate different salts. Okay? But then, as far as I know, these systems are not really large systems. They are industrial type of system, but for large systems, you need to be robust, and then you lose the economical aspect. But for membrane, yes, for membrane system, you can select. So actually, there are like the Voltaire systems. There are membranes and capacitive deionization. There are systems that are exactly focusing on selective removal. But normally, you already know much better. Normally, these systems are also not for very large production. They are not systems for, like I said, for a city of 2 million, 5 million. I'm talking more here as a civil engineer with civil engineer eyes, more for these type of human consumption type of systems. And then you lose selectivity because you need to produce 60 cents per cubic meter. Yeah. Good question. I have also papers that I mentioned in the presentation, guys, right? So what I would do, Jordi and Uchi, together with the presentation, I make a PDF of the papers as well. So you're gonna get the papers and you get the presentation. So the students interested in reading the papers as well, you have access to it. So you can put in some kind of share folder. Yeah. Thank you very much. Yeah.
Thank you, and see you on Thursday.
See you Thursday. Yes.